Everybody. I'm the recording has started. Let me try that again. Hello, everybody. My name is Matt. I'm a fifth-year graduate student in the department here, Department of Physics at the University of Washington. I recognize a lot of familiar faces in the audience, so hello to everybody. Yukari, if you could do me a favor and handle people entering the waiting room. I don't
Yeah,
think I have the
yeah,
coordination to do
yeah,
that and speak at the same time.
yeah, I will do that.
Um, yeah, okay. Today I'm going to be talking about neck rupture and scission neutrons in nuclear fission. Um, I welcome questions over the course of the talk. I can't promise I'll be able to answer all of them, but if there's, I'll stop at a few moments and offer people the opportunity to ask questions, but I encourage that during the talk itself. Okay, so with that, let's dive in. I want to give a brief outline of the talk. We're going to go over an introduction to nuclear fission. We're going to go over sort of a detailed anatomy of the fission process. Then I will present our results on scission neutrons and prospects for experimental detection, and then I will outline future work. The reference for the paper that we'll be discussing is at the bottom here. This was published in Physical Review Letters in 2024. And my collaborators on this project are Aurel Bulgac, who's the PI from the University of Washington, and also Yanel Stetku and Ibrahim Abdurrahman at Los Alamos National Lab. Is the audio okay? Everybody can hear me and everything? Okay, excellent. You guys are over in this direction, so when I'm looking this way, I'm looking at you, just for reference. Okay, so brief history and motivation of the fission process. So this is a nuclear reaction, and we have sort of a cartoon image on the right of what takes place. So we have a uranium-235 nucleus. There's a neutron, which comes in, the uranium nucleus swallows it up, it forms this uranium-236 compound nucleus excited state. It then breaks apart, and it gives off two atoms, which we call fission fragments. It also releases approximately 3 neutrons and some photons as well. So this reaction produces a lot of energy when compared with other nuclear reactions and chemical reactions. The typical energy scale for a chemical reaction that gives off energy is something like 10 electron volts, but the kinetic energy of the fission fragments is 170 mega electron volts. So we have a factor of 10 million between a single fission reaction and a single chemical reaction. Within other nuclear reactions, the difference in energy scales is obviously not this stark, but still it's quite dramatic. Nuclear fission was discovered in December of 1938 by Otto Hahn and Fritz Strassmann. They were bombarding a sample of uranium with a beam of neutrons, and then in chemical analysis of the products, they observed barium. Uranium has 92 protons per nucleus, and barium has 56 protons per nucleus. I have to imagine that this was something of a surprising discovery because at the time there was no known mechanism by which such a process could take place. And just 1 month later, which is sort of, I don't know, it's kind of interesting when you think about what modern academia looks like. But 1 month later, Lisa Meitner and Otto Frisch published the theoretical explanation. I mean, at the coarsest level of what was going on, that the nucleus has split roughly in half. One observation which follows from this is that since it takes only one neutron to induce a fission reaction, and each reaction produces more than one neutron on average, this creates the possibility for a chain reaction where one fission induces several, each of which induce several, and then you have some sort of runaway process. The notion of a nuclear reaction was introduced by Szilard in 1933, which you'll notice is before the discovery of fission. It was understood that this as a general kind of process could take place before fission was discovered, but it was shortly after fission was discovered, it was understood that this could apply to fission as well. So the chain reaction is really where most of this becomes relevant for society, let's say. So if you have a controlled chain reaction, then you get a nuclear fission reactor. And if you control your chain reaction, you can use that to produce heat, and that therefore can act as a source of energy. But you can also use nuclear reactors to produce neutrons, photons, or radioactive isotopes for scientific, engineering, medical, or military applications. If you have an uncontrolled chain reaction, that's what a nuclear weapon is. And there are sort of related issues pertaining to national security. So if you have a detailed scientific understanding of the process of nuclear fission, you understand the kinds of radiation that are given off. For example, you can detect whether someone has detonated a nuclear weapon somewhere in the atmosphere, or as trying to smuggle a weapon across your border or something like this. So there are practical applications to having an understanding of a detailed understanding of fission. But as scientists, this is not primarily what motivates us. We're interested in fission because it is a quantum mechanical phenomenon of immense complexity, which still lacks a complete microscopic description to this day. So I'm going to say in a little bit more detail what this means and sort of take three perspectives as to why, from a scientific perspective, we care about the theory of nuclear fission and fission in general. So there's sort of the fundamental physics perspective. I use fundamental in air quotes only to distinguish that I'm not talking about beyond standard model physics or something like this. I just mean sort of describing the physics from a fundamental perspective. And viewed from this lens, fission is a strongly interacting quantum many-body process out of equilibrium. So I've colored each one of those terms separately because each color adds immense difficulty and fun to the scientific problem. You can think of each color as basically being sort of a separate graduate level textbook that all interact in interesting ways when you have to try to think about fission. And to be a little bit more precise about what the problem we're trying to solve here is, it's to calculate all properties of the nucleus and its dynamics and the properties of the emerging debris, starting from the basic laws of nature. And I'll say a little bit in detail. I'll try to give you a more precise picture in the next couple of slides as to what such a picture might look like. From an astrophysics perspective, so this is another scientific motivation why fission is interesting. Oh, Yukari, I realize I did not start my clock, so I do not know how long I've been speaking for. I might chime in at various points to ask you how much time I've used up, if that's possible.
Yeah, it's like been 6 minutes, but you can
Okay.
put on there and it's fine.
We should be good. I think the talk will not use up the full time, but I might ping you at some point. Okay, so from an astrophysics perspective, there are two kinds of astrophysical processes, at least where fission becomes relevant, and each one of them has an associated picture on the right side of the screen. By the way, can people see my mouse?
Yes.
Okay, cool. I will use it to refer to things over the course of the talk. So in the top image here, we have a supernova, which you can see is this bright point here, which is shining as bright as this galaxy in this image here. And on the bottom, we have a neutron star merger. This is an artist's rendition. So in these two kinds of extreme astrophysical processes, you can produce large quantities of unstable neutron-rich nuclei through what's called the R process, or the rapid neutron capture process. And this R process is believed to be responsible for the origin of half the elements in the universe, roughly half the elements in the universe, heavier than iron. And this is an ongoing topic of exploration for for precisely how that comes about. And fission is one of the primary pathways by which these unstable neutron-rich nuclei decay towards stability. And then there's also a study, which is somewhat related but distinct, of super heavy elements and the synthesis of super heavy elements, where the fundamental scientific question is, what are the heaviest elements, which is to say nuclei, that can possibly exist in nature? So there are a number of experimental groups all over the world. They perform nuclear reactions to try to synthesize these super heavy nuclei, which can roughly be thought of as trying to extend the periodic table of elements. I believe the last element, oganesson, was added to the periodic table in 2003, although I'm pulling that from memory. So if I'm slightly wrong, my apologies. And again, in this case, fission, particularly spontaneous fission, is one of the primary decay pathways for the super heavy elements. Okay, so hopefully I've motivated to you all why we as physicists in the 21st century should care about the fission process. Next, what I'm going to do is I'm going to do a deep dive on the anatomy of the fission process and go over everything that takes place in detail, but now would be a good time to ask a question if anybody has one. You do not have to ask a question. Okay, speak up, otherwise I'll keep going. Okay, so let's go over in detail the fission process. And I have two complicated figures here, but we're going to spend a long time, so we'll be able to understand everything that they have to say in detail. Okay, so let's first draw our attention to this figure on the top here. So we have time moving left to right. And the purpose of this figure is to just sort of outline all of the various pieces that go into the fission process. So we'll go over it quickly and then slowly. So the first thing that happens is we have a nucleus, say uranium, which is sitting here, and a neutron comes in and the nucleus absorbs that neutron. Then the nucleus will sort of elongate and eventually split apart. And then after the nucleus splits apart, these two things are positively charged, so they repel one another and they fly away. The nucleus will release neutrons and then gamma rays, and then to further decay to stability, you will have beta decays. Okay, so this is the very broad high-level overview of the process. And again, I apologize to do it this way, but I'm going to drown you with a little bit more information, and then we're going to, like I said, go over this much more slowly. So here we have the energy of the nucleus as a function of the elongation of the nucleus. So you can see these little cartoon images here. As the nucleus gets more and more elongated, this red curve is supposed to indicate sort of the ground state of the nucleus as a function of its deformation. Okay, so that was too much detail, but now let's go over it more slowly. So hopefully we can internalize much more of this. So the first stage here, this is the entrance channel moving from this frame to this frame, basically. Nucleus of a heavy atom absorbs a neutron and it moves to what we call the outer saddle point. The outer saddle point refers to this point here on this, what we call the potential energy surface, the energy versus deformation, where the nucleus looks roughly like this. So I'll refer to the outer saddle point at a number of times during the course of the talk. The nucleus will look like this. The time it takes to evolve from the ground state to the outer saddle point is something like 10 to the minus 14 seconds. And this can be understood as a quasi-equilibrium process. And we should keep in mind that when the nucleus is in its ground state, it is cold and it has a small spin. Okay, so the next stage of the evolution, we've now made it to this frame here. We're going to describe moving from this configuration to this more elongated configuration right when the nucleus is about to split apart. This is called the saddle to scission evolution. Scission is a word that's going to come up a lot today. It's the process where the nucleus actually goes from one shape to two shapes. So that is the moment of scission. So as we go from the saddle point here to the scission point, this is a much faster process. This takes place over the course of 5 times 10 to the minus 21 seconds, roughly speaking. This is a highly non-equilibrium process where the collective velocity of the nucleus is small and the nucleus heats up. Okay, so that's moving from here to here. And then we have the next stage here, which is scission, which is also referred to as neck rupture, which is somewhat graphic term, but these are the terms that we have. And that's moving between this frame here and this frame here. So where the nucleus actually breaks into two pieces. This is the fastest stage of the nuclear dynamics. It takes place over the course of roughly 10 to the minus 22 seconds. Again, this is a highly non-equilibrium process. I have in bold here, this is the stage where the scission neutrons are released. That is the claim that we're making, and I hope that I'll provide you a convincing argument that this is the case over the course of this talk. You can make your own conclusions. And I also want to indicate that this is the fastest stage of the fission dynamics. Okay, so we've made it from this blue square here to this frame here. So the next thing that happens, same diagram, so just have more bullet points, is the fission fragments accelerate due to their to the Coulomb interaction. So these two nuclei here are positively charged, so they therefore repel each other. And this takes on the order of 10 to the minus 18 seconds. Again, this can be thought of as a quasi-equilibrium process. The fragments might emerge in a deformed state, but as they're accelerating away from one another, the shapes relax, and the fragments are now hot and rotating rapidly. They have a high angular momentum as opposed to the nucleus in its ground state, which was cold and had a low angular momentum. And now we have these hot fission fragments that are flying away from one another, and they emit neutrons, and we'll call these prompt neutrons, although the term is not perfect, but for the sake of this talk, we'll refer to these neutrons that are released as prompt neutrons to differentiate them from the scission neutrons. And this should be understood as an evaporative process. We have these fission fragments that are flying away from one another. They're hot, which means some of the nucleons have high velocity, and therefore they can be evaporated out of the fragments and released. 10 to the minus 14 seconds, if I didn't say this already. Now we have these fission fragments with a slightly lower excitation energy, but they're still in excited states. So they will further de-excite, and therefore, and in so doing, they release gamma rays. And this can happen 10 to the minus 3 seconds might be a slightly extreme end of the range. This diagram here has 10 to the minus 14 to 10 to the minus 7 or so. So Okay, so that's where the gamma rays come from, and then still, you might have a nucleus which is not in sort of a more stable state, so you can have further beta decays, and in very extreme cases, you can get long-lived metastable states, which can have lifetimes sometimes on the order of billions of years, although that is certainly an extreme case. All this to say, you can have something like 40 orders of magnitude in time scale relevant for the fission process. And even if the very long-lived beta decays, you don't want to consider those, then you still have something like 25 orders of magnitude, something like this. So I hope through this description of the fission process, you can understand my claim that this is a highly complex process for which quantum many-body physics is relevant. There are aspects which are out of equilibrium. It's quite a complex thing.
Can I
Okay.
ask?
Yeah, please, please.
So you have these like bunch of like time scales, like from 10 to the minus 22 to 10 to the minus 3. Like, how are these numbers obtained? Like from experiment or like from theory calculations or?
Well, certainly some of them cannot come from experiment. So I guess I should have mentioned this, but these two bullet points here, saddle decision and neck rupture, which is basically these three red frames, these numbers are ours, and they come from our theoretical calculations. Basically, almost all of the timescales that I've listed in these figures are so fast that your experimental detector will never be able to have time resolution on these timescales. So my understanding is that most of these numbers will come from theoretical calculations, although I'm not responsible for producing all of the timescales myself. So it's possible that the beta decays and gammas, I guess I know the least about those, but I believe that most of these are numbers that have to come from theory.
Okay, thank you.
Okay, thanks. Any other questions? Thank you for being the first to ask a question. Okay. All right. So moving forward, I'm now going to spend a bit of time on the particular theoretical approach that we use. This is called TDSLDA, which stands for the time-dependent superfluid local density approximation, which is a big mouthful. It is based fundamentally on density functional theory, so I'll just say a little bit about what this is. Density functional theory is a general theory for interacting fermionic many-body systems. In this case, our fermions are our neutrons and protons. And just an interesting sort of aside, this density functional theory was basically founded in these two papers by Hohenberg and Kohn, and separately Kohn and Sham. And if you look on Google Scholar together, they have something like 143,000 citations, which is absolutely monstrous. To give you an indication of how high impact this technique has been for fundamental science. And the best description of this process I've found for time-dependent density functional theory in particular comes from E.K.U. Gross, who is one of the co-discoverers of this technique. So I'm going to quote this exactly. Time-dependent density functional theory can be viewed as an exact reformulation of time-dependent quantum mechanics, where the fundamental variable is no longer the many-body wave function, but the density. Now, this is a technical point, but it solves a crucial problem because the many-body wave function, generally speaking, is a function of n variables, which in the general case is totally intractable from the perspective of representing it on a computer, say. But the density is a function of just a single variable, your coordinate in space, say, and that's a much more tractable problem. So it renders this quantum many-body problem, in principle, tractable. Okay, so TDS-LDA is an extension of time-dependent density functional theory to superfluid systems, which nuclei are superfluid systems. That's sort of a story that I'm not planning on going into today, but it's an interesting story. And TDS-LDA is one of the most advanced theoretical approaches available for studying nuclear fission dynamics. It can also be used to study nuclei more generally at low energies, as well as cold atom systems, the crust of neutron stars, quantum turbulence, etc. And for all of them but quantum turbulence, you can study this in equilibrium and out of equilibrium. So it's a very flexible theoretical technique, and it relies on only 8 parameters, which are derived from 8 parameters from nuclear physics, all of which have been known for decades, and none of them were derived in the context of nuclear fission. So I hope I've argued to you that this is a very powerful approach, but let's say exactly what it can do. So the reason why I'm going over this is because we have a single formalism which can be applied to the entire nuclear chart here. So for those of you who have not seen something like this before, although many of you many of you will have. This is basically the set of all nuclei which are known to exist, approximately speaking. We have the neutrons on one axis and the protons on the other axis. So we have some big set of nuclei. And this one formalism can be used to calculate static and dynamic properties of most of these nuclei at low energies across the nuclear chart. I say most because if you start getting lighter than oxygen, the accuracy of the predictions gets worse. But it's a single approach which allows you to calculate the properties of many of these systems with good accuracy. And I will say also, once you specify the functional, which involves these 8 parameters that I mentioned on the previous slide, there are no more decisions to be made. So from this, you take a derivative and you derive the equations of motion, and then you start with an initial condition, and then you simply solve the equations of motion to calculate the ground state or to time evolve the system. So once you specify the functional, everything else is determined. And I guess I'll say one more thing, which is for those people who have not thought very much about the functional, you can roughly think about a functional as being analogous to sort of a Lagrangian density, where you specify the various ingredients that you want your physical theory to have, and then there's a well-defined procedure for calculating the equations of motion from there, and then we solve them. So using this functional, again, that's a lot of technical details, but it might be interesting for some of you. So using this particular functional, which we call SEAL, we have among the best descriptions of a variety of nuclear properties, again, over the entire nuclear chart, including masses, charge radii, compressibility, surface tension, et cetera, et cetera, et cetera. There's a lot of properties here. So it's a very flexible approach. And the only thing that you need to change to go from one nucleus to another is you change the particle numbers, and then you change the size of the box to make sure the nucleus can fit. And like I said, after that, everything is simply solving the equations of motion. In particular, in the context of nuclear fission, this theory has had a number of successes. So for one thing, scission was achieved starting from the outer saddle point with very little excitation energy. So as a reminder, scission means the nucleus actually breaks apart. So the nucleus is started in some deformed configuration. I'll actually just remind you briefly. So we start here where the nucleus looks something like this, and then we simply time evolve the equations of motion from there with very little excitation energy, and the nucleus breaks apart. Okay, so that was one significant success, which had been accomplished by other groups in the past, but you have to make certain sacrifices. And this was accomplished basically because pairing was treated properly, which allows for repopulation of states as the nucleus elongates. And it turns out that if you don't allow for repopulation of states like this, then it would take far too much energy to get the nucleus to fission. The fission barrier will be off by something like 200 MeV. And for those of you who know, the fission barrier is something like 10 MeV. So that's a pretty large error. And I'm pretty sure the person who figured this out is actually on this Zoom call, which is pretty cool. Anyway, moving past that, so that was one of the major achievements of this. Another major achievement of this formalism was it demonstrated that the so-called adiabatic approximation is strongly violated. And I'll spend a few minutes now explaining precisely what this means, or I'll do my best to explain precisely what this means. The first thing I'll say, though, is that this was an approach which was widely invoked in the literature studying the fission problem, and we now we've presented a strong piece of evidence that this should be challenged. This way of thinking should at least be challenged. So let me say briefly what this is. Over here, I have a plot of the potential energy surface, which is closely related to this figure here. So on the horizontal axis, we have the elongation of the nucleus, and then we have the energy of the nucleus on the vertical axis where we've subtracted off its kinetic energy. So we have this energy surface here, and the adiabatic approximation will say, or I guess I'll imagine you to go through a little exercise. Imagine that you have a frictionless point particle sitting on this hill. It has some potential energy associated with it, and you let it go. And then, whoops, my mouse disappeared. Under gravity, it will slide down this hill, converting that kinetic energy, that potential energy into kinetic energy. So if you were to subtract the kinetic energy, then you would recover this hill. So you take the total energy, you subtract the kinetic energy, and all you're left with is the potential energy, which is this hill here. But we can actually time evolve the nucleus according to the TdS-LDA equations. And what we see is something like this. Okay, I guess it starts up here, but the story is the same. So one would have thought that it's sliding down this hill, but if you subtract off the kinetic energy, you find that the remaining energy is very close to the starting energy. So the only place that this energy could possibly go is into internal excitation energy of the nucleus. So rather than sliding down the hill and converting everything to kinetic energy, it goes to heating the nucleus up. And it's not moving very fast. So most of the energy goes into internal excitation energy. And this is something that we can check explicitly with TdS-LDA, and we find that it is a dissipative process. And I should also say that we're not the first ones to suggest that this should take place, but this is strong evidence that the adiabatic approximation is strongly violated, as I say. And I'll bring up two more pieces of evidence here, and then I'll make a brief remark. Some other things that the code has revealed is that the light fission fragment emerges from fission hotter and with a higher angular momentum than the heavy fragment. The hotter part is kind of interesting because you imagine you have something which is 10 to the minus 14 meters across, it breaks apart, and one half is hotter than the other half. So that something interesting is taking place there. And also, we've predicted or we've calculated that the fission fragment intrinsic spin should not be perpendicular to the fission axis. And I have a bullet point here that says both of these points contradict assumptions used by other leading phenomenological approaches. And I want to just stop here and make a brief remark because I've given a talk about this before. And I raised these points that we have disagreements with other groups, not to just cause trouble or something like this. So let me just say a little bit about why I bring this up. So again, I'll return to these slides where we have all of the full complexity of the fission process in one place here. This is a supremely complex phenomenon, fission. Our codes are focusing on this region here, but if you're an experimentalist, you'll put, I mean, I'm not an experimentalist, but my understanding is that you put a sample of uranium or plutonium or something like this in a detector, and then you have various detectors that are either looking for neutrons or gammas or fission fragments, things like this. So if we're only simulating out to 10 to the minus 21 seconds or something like this after the moment of scission, that's a long way to go before you have neutrons and gammas, which are the things that will be observed by the experimentalist. So we have to work hand in hand with people who have codes that are focusing on different stages of the dynamics. And the reason why I bring up the point where we run into issues, or not issues, we run into inconsistencies with some of these other approaches is because we can have sort of this harmonious interplay where certain people start with a set of assumptions and they make useful predictions. We start with a different set of assumptions, and then we can calculate to the point where our code meets up with sort of the next code in the chain. So the point where these things result in differences can be a valuable point of conversation with groups that have other approaches. So I want to be precise about this because it's not the only time that I'm going to mention places where we come in contact with other groups. And it takes everybody to make valuable predictions here.
Can I ask another question? Thank
Yeah,
you.
sure, please.
Nice remark. So your code starts with the place where outer saddle point, right? What do you call outer saddle point? Where like the
Yep.
breaking is kind of starting to happen already.
Yep.
And this is your like initial state already.
Mm-hmm.
How
Yep,
do
correct.
you get this initial state? Like I can probably like imagine like what the ground state of uranium like 136 is going to be like, but I don't know.
Mm-hmm.
How does this look like, as a sort of quantum, like say wave function? So how do you get that?
Yeah. Okay. I mean, I can answer at like a detailed, how do we implement this to get a nucleus that looks like this? But that's probably not the question that you're asking. So we're starting something like this. So this is a stage of the process which I don't spend nearly as much time thinking about, but my understanding of what takes place here is that the nucleus absorbs this neutron here, and that induces sort of a slow vibrational kind of process where you're vibrating around a spherical shape. And eventually, again, the knowledgeable people will know that this is a cartoon of the full story, but this is the picture that I understand. Eventually, it will oscillate to a state like until it has sort of a deformed configuration like this, at which point, the Coulomb repulsion between the left and right half are trying to push it apart so aggressively that the surface tension can't sustain that anymore. And that's what ultimately causes fission. So the assumption that we're working under is that there will be some dynamics which get you from this ground state configuration where you have a roughly spherical looking nucleus to some deformed configuration. And from there, that's where we start evolving. There's a more principled way to do this. Since you ask, I'm going to make everybody motion sick by scrolling all the way to the end here. This is a two-dimensional version of the potential energy surface. So on the horizontal axis, we have the elongation of the nucleus, and on the vertical axis, we have the left-right asymmetry. So you imagine you can elongate, and you can also sort of like squeeze it one way or another. And you'll see, and each one of these red curves is a fission trajectory. And eventually they all flow up to the right as the nucleus splits apart and gets elongated and everything. And the points that we typically choose are along, I guess you would call this sort of the outer rim, but it gives a little bit more meaning to the term saddle point, because at around this point on this surface, everything becomes unstable and all of the trajectories will flow towards fission. So we choose points along the outer rim here, under the assumption the ground state, which is down here, that there is some process by which the nucleus evolves from the ground state to the outer barrier before it undergoes fission. And that's a story for another day. Like I said, it's like 10 million times slower or something. So
Okay. Yeah. Thank you so much. Yeah. Sorry.
yeah, sure. Are there other questions? It's a good question. Okay, I'm going to go back. Sorry for the rapid scrolling again. I promise I'm getting to scission neutrons. How am I doing on time, by the way? Is that 35 minutes?
Yeah. 30 minutes so far.
Okay, then I've got to speed up. Okay, actually, that's perfect. So scission neutrons, this is the reason ostensibly we're all here. So that was an introduction to fission in all of its glory. Now let's talk about scission neutrons, which is the result that I want to present about today. So I'll draw your attention to the figure on the right here. So we have a uranium-236 nucleus, and time is moving down the page. And hopefully you can see at 0th order, this nucleus is breaking apart. This is a slice through the neutron density, and we're plotting it in log scale. And hopefully what you can see is that there is some low density cloud of particles of matter that appears to be emitted around the nucleus as it breaks apart. So let's say it breaks apart at this frame here, we start to see there's some matter released transverse to the fission axis. And in fact, this is a two-dimensional slice. So this should be understood as a ring-shaped cloud that's emerging around the neck as it ruptures. And then with a slight delay, we start to see a cloud of neutrons emitted longitudinally along the fission axis. And eventually we get to a point where this cloud propagates outward and it reaches the boundaries and we get some interference effects. Okay, so this low amplitude cloud of neutron matter that is being released from the nucleus in our simulations, we claim are the scission neutrons. And I'll say a little bit about more precisely about what this means. So scission neutrons were conjectured to exist as early as 1939 by Bohr and Wheeler. They're talking about a fluid mass of unstable form, which divides into two smaller masses of greater stability with little tiny droplets left over. So this was their quote. To be clear, this was a conjecture. They offered a number of possibilities, but this was one of them. And it's interesting that this is the same year that they discovered fission was taking place. So people have been actively publishing on the topic of scission neutrons for over 85 years. And it's a contentious history. No consensus in the literature from experiment or theory as to whether scission neutrons should exist even now. So here we're presenting arguably the first fully microscopic time-dependent simulation of the phenomenon. Fully microscopic will mean different things to different people, but let's call it highly principled microscopic calculation here. What I hope is clear from this image is that the scission neutrons are clearly present, and they're present for free. which is to say, we did not go out searching for scission neutrons. We did not kick the system or perturb it in any way. This was something that we noticed after running time-dependent fission calculations. Hey, doesn't it look like there's a cloud of neutrons being given off by the nucleus? Isn't that interesting? I wonder if this is this phenomenon that people have been discussing for so long. And another thing that's worth noting is scission neutrons have been observed in all TDSLDA fission calculations which have been performed to date, and that number is going on is almost 200 at this point. So we've done a lot of fission calculations, and they're present everywhere. Okay, further details about this figure, which are interesting. Hopefully you can see that this has a distinctive angular distribution where, like I said, we have this ring-shaped cloud which appears around the neck, and then we have these longitudinal clouds. And it's also a fact which I'll demonstrate to you, I think, in the next slide or in a few slides, that there are equal numbers. So in the longitudinal cloud and in the ring-shaped cloud, there's about the same number of particles in each. And this is different from, you'll remember I defined those prompt neutrons earlier. So the fission fragments have been Coulomb accelerated from one another, and then they evaporate off neutrons. So it's thought that those evaporated neutrons have an isotropic distribution in the rest frame of each fragment. And these neutrons have a clearly different distribution. It's not isotropic at all. It has these distinct sort of prongs to it, or that's not a great term, but it has these distinct subclouds to it. And they're released essentially from a stationary compound as opposed to these fully accelerated fragments. And this angular distribution is observed for all the nuclei and trajectories we considered thus far. So we looked at U-236, plutonium-240, and californium-252, and all of them had the same general shape to the neutron cloud. Numbers amount to 9 to 14% of total emitted neutrons during the fission process. And I'll substantiate that last claim more in a few slides. So the scission neutrons are released during a small interval of time while the neck heals imperfectly after the rupture. So the rupture takes place basically here. It hasn't ruptured in this top frame, and in the second frame it has ruptured, and you see some of the neutron matter just doesn't get swallowed up into the fragments. And we mentioned this in the paper. It's somewhat like, but not quite like, a balloon popping in the air flying out, because you have sort of this viscous fluid with surface tension and things like this. But it's an imperfect healing process that ultimately gives rise to the ring-shaped cloud. And then there's a second step here. I have in parenthetical that Bohr and Wheeler are postulating a different mechanism, so we don't agree with them. They were a bit ahead of us by 85 years, but anyway. So in 1985, Madler suggested a possible mechanism for scission neutron emission, which he called the catapult mechanism, which we're offering a correction to call this a slingshot mechanism, which we believe actually does hold. So we've offered an explanation for where the ring-shaped cloud around the fission axis comes from, but then we have a delay and then the longitudinal cloud emission. And the hypothesis here of the slingshot mechanism is that it is the absorption of the neck into the fragments, which is a rapid process, and it pushes neutron matter through the fragments and then out the front of them. So that's why there's a delay followed by this longitudinal emission here. That seems to be a plausible interpretation of the data. Okay, let me just remind myself exactly where I am. Yep, so we talked about that mechanism. Oh yes, and another thing to note here is that the scission neutrons are high enough velocity that the fission fragments will never catch them. So you can calculate the final velocity of the fission fragments, and you can calculate the velocity of the scission neutrons, and you can determine that the fragments will never catch them. So this means that these neutrons will escape to infinity because there's nothing to catch them. So in principle, they should be detectable experimentally. So that's exciting. So there's some prospect of checking us on our claim that we believe these exist. You might be able to, in fact, see them in a detector. And also, we can estimate the interaction energy of this cloud of scission neutrons. We find it to be essentially non-interacting. So we believe that, for example, something like a condensation to a third nucleus is unlikely, although I want to stress that our formalism can't actually describe condensation itself, but in order to have condensation, you need to have a three-body collision, and since the number density is so low, that should be an exceedingly unlikely process. So if you're looking for an explanation of 3 fission fragments instead of 2, I believe sorry, if you're looking for an explanation of how you could end up with 3 fission fragments instead of 2, it is unlikely to be this process that we're describing here. Okay. So now there's the reasonable question of how many are there? And I mentioned earlier that it's 9 to 14%. But here I can be a little bit more precise. So here we have time after scission, and then we have the number of particles emitted. And I mentioned that we have U-236, plutonium-240, californium-252. And I'll just draw your attention to these solid curves first. And we see that there's some increasing function of time, and maybe they start to level off. Arguably, californium is not leveling off. The width of these curves is mean plus or minus 1 standard deviation. We perform something like 5 calculations per nucleus, starting from different initial deformations. And these, you'll notice the number of particles is not an integer because these are average particle numbers that we're working with. And given that the average number of particles emitted, of neutrons emitted during fission is something like 3-ish, that's where we end up with this number 9 to 14%. Although I stress here, it's likely to be conservative, especially in the case of California, which seems to still be increasing. I mentioned, oh yes, so then these dashed curves are the proton numbers as well. So I haven't mentioned this, but it is the case that we observe a small cloud of protons being emitted during scission as well. These curves are amplified by a factor of 10 because the signal is much smaller. It's about 1/50th, and I'll return to this point because it seems to be slightly problematic, actually. I have this figure on the bottom here just to indicate we have this distinctive cloud shape, and I mentioned that there's roughly an equal number of particles in longitudinal emission and in the annular emission around the nucleus. So if we separate perpendicular and longitudinal, these blue and purple curves, you'll see they fall right on top of each other for the case of uranium, and it's basically the same for the other nuclei as well. So that's the claim that there's roughly equal numbers of neutrons emitted along the fission axis and in a ring transverse to the fission axis. Okay. Again, please chime in with questions at any time if people have them, but I'm going to just keep going if nobody speaks up. Okay. Next aspect of this, we can estimate the kinetic energy of the scission neutrons. So here are some numbers for the average kinetic energy per neutron of the scission neutrons. I'll just draw your attention to the figure here. So what we have is our estimate of the probability distribution of the kinetic energy per neutron. Okay, so we have the energy per neutron on the horizontal axis. This is the probability. We see that there's very little probability at low energy per neutron because if it was sufficiently low, those neutrons would still be inside the fragment. And obviously we don't consider them if they're still inside the fragment, they're not scission neutrons. So we see that there's a peak at some energy, which is around 3, and that's where we get these averages. But we do expect that some small fraction of the neutrons emitted will have a considerably higher kinetic energy, going up to something like 17 MeV. And this is another point where I want to connect with some of the other sort of codes that people use in the community. This high energy tail, small number of neutrons which are emitted, which may be emitted with high kinetic energy, might be relevant for the spectrum of all neutrons which are emitted. So one of the leading codes that is used to calculate what you expect to see in neutron emission from fission is this code called CGMF. And within CGMF, they don't have enough high energy neutrons. So it has been suggested that we might try to incorporate the high energy tail from the scission neutron study to see if we can correct the CGMF code and see if that high energy tail is more properly described. And the appropriate people know about this data and have considered, excuse me, have talked about incorporating this data into CGMF, but I don't know what the status of that is. So something to be seen in the future. And I just want to emphasize as well that the evaporation of neutrons from the fully accelerated fission fragments are very unlikely, basically cannot account for neutrons of very high energy like we're seeing here. Okay. Whoops, did I skip anything? Nope. All right, so now I want to talk about the dynamics of the neck here. So we have two figures over here. I'll first draw your attention to the top one. So this is the fission axis on the horizontal axis. And all we've done is we've projected the density onto the z-axis. So we integrate over x and y. And then we have three time slices here. The black curves are the initial times. The red curve is some intermediate time around scission. And the blue curve is some later time after the nucleus is split apart. So the blue curve, you can see two separate humps of density, which correspond to the fragments which have separated. And the black curve here, the initial state, you have some compound nucleus, some compact shape here. And the reason why this figure is of interest is because we see that this is close to the outer saddle point, where the nucleus, let's say, is slightly peanut shaped, but it by no means is it particularly close to actually breaking apart. But even so, there's this noticeable dip when you plot the density in logarithmic scale, and then as time evolves, that dip does not move in time. And this might be a little bit primarily of interest for the theorists here, but this contradicts another one of the phenomenological models, which is called the Brosa model. And let me just say briefly what this does. So one of the problems if we are a theorist trying to discuss the problem of nuclear fission is you want to try to determine the particle number distribution of the fission fragments. So your nucleus breaks apart, you start with the uranium-236 or something, it breaks apart, and then you have an atom here and an atom here. There's a question as to what is the identity of those atoms? How many protons and neutrons do they have? So you imagine there's some probability distribution of neutrons and protons. And that distribution, there's a wide range of possible atoms that can break into. So one of the obvious challenges for us as theorists is to try to predict the particle number distribution of the fragments. One such approach which can accomplish this is called the Brosa model. And my understanding of how this works is you take a nucleus, you consider it to be in some highly elongated shape, and then somewhere along the neck at some random location, you chop the nucleus. And you imagine the randomness can give you a distribution of particles in this fragment and a distribution of particles in this fragment. And all this to say, the microscopic calculations do not substantiate the notion that there's a random location for the rupture of the neck. The neck location is determined early, basically at the outer saddle, and it does not move as you evolve towards scission. So maybe only of interest to the theorists in the crowd, but moderately interesting nonetheless, for the reasons that I mentioned earlier when I discussed the other sort of phenomenological approaches. Once the neck reaches a critical diameter of 3 Fermi, a different set of dynamics take over and it rapidly splits apart. For the reasons that I mentioned already, you have these two charged fission fragments that are close to one another. There's a surface tension which wants to keep the nucleus together, but the Coulomb force is stronger than the surface tension in that configuration, and it splits apart. And we see from this bottom figure here that the neck dynamics are basically universal with quotes and an asterisk. So I'll mention what both of those symbols are for. But there's a high degree of sort of conserved regularity to the dynamics of the neck. So what this is this is time around the fission at time around the moment of scission on the horizontal axis, or excuse me, this is imprecise language. This is time around scission on the horizontal axis. And then what this on the vertical axis is, it's basically taking this midpoint of these curves here, where we know the neck is going to form, and just plotting this midpoint as a function of time. And right around the moment of scission, it's clear that there's sort of a conserved character to these dynamics. And you see this is a log scale on this axis and a linear scale on this axis. So this is an exponential decay, and we can assign a decay time scale to this process. So we find that the neck rupture times are roughly 35 Fermi over C for neutrons and 15 Fermi over C for protons. So this goes back to this claim that I made earlier in the talk that neck rupture is the most rapid stage of the dynamics. You'll remember that a Fermi over C is roughly the time it takes for light to cross the size of a nucleon. So that's a really short time scale. A Fermi over C is 10 to the minus 24 seconds or something like this. And for comparison, the time that it would take to communicate information between the fragments, roughly speaking, is 160 Fermi over C. You can estimate that in slightly different ways, but no matter how you do it, you're going to end up with something that's longer than these two timescales here. And another thing that's worth noting is that the proton neck ruptures faster and it ruptures first. So you'll notice that the proton neck is basically ruptured by this point here, and then you have 100 Fermi over C, where the neck between the two fission fragments is entirely supported by neutron matter, which is kind of interesting. Um, okay, so I mentioned I would put the air quotes in the asterisk. So the air quotes, we're not married to this notion of like, this is universal. You don't have to assign too much meaning to that word other than the fact that you start with very initial deformations, and the nucleus may do different things as it evolves towards the point of scission. But once you get to scission, these dynamics appear to be the same for asymmetric fission. Future work, we're going to be looking at symmetric fission, and there's some preliminary indications that maybe this does not hold in the case of symmetric fission, but stay tuned for that. Okay, so a brief word about numerics. I've got 8 minutes left. Is that right, Yukari? Okay. How's that looking? That should be fine. Um, we'll get there. Okay, so I mentioned a little bit that we have these interference patterns, like the neutrons at a certain point hit the boundary of the box. So why don't we just put this in a bigger box? Reasonable question. But I will say that these were the largest simulation box ever considered for this kind of technique in order to follow the emitted particles for as long as possible. So these are technical details, but for computing kinds of people, you might find this interesting. These were enormous simulations that were required. We were simultaneously using 27,648 GPUs for 15 hours straight for a single time-dependent trajectory here because the boxes were so large. We're using the entirety of the Summit supercomputer to do this in 2022. Summit was at the time either the largest machine or in the top 3 for the largest supercomputers around. And so our sort of like sensational newspaper headline is that this was plausibly one of the largest computations that's ever been performed in human history. Now, I will say you can always make a computer work really, really hard and have it do nothing useful, but this was strictly necessary to solve this problem. And for, again, a few more technical details, for preparing the initial conditions, we had to repeatedly diagonalize a matrix of double complex numbers, which was of size 1.1 million by 1.1 million, which is enormous. And then for the dynamics, we had to solve 4.4 million coupled nonlinear complex valued PDEs in 3D plus time for 40,000 time steps. This produced 89 terabytes of new wave function data at every step with good energy conservation, good particle number conservation. So quite the computational feat from my perspective. Okay, so I mentioned that I would talk about scission protons, so let's discuss this. So you will, at this point, recognize this figure. This was our preliminary evidence that the scission neutrons exist. And these are the neutrons in the left panel, but what I'm also plotting in the same scale is the proton density as well, again, logarithmic scale. And what we see here is that in the longitudinal sort of direction, there is a low amplitude cloud of proton matter that's released as well. I mentioned already this is 1/50th the level of the neutron, so it's a very small number of particles, but it's a problem. So we've spoken with some experimentalists, and they've told us that longitudinal emission of protons would very probably already have been seen if it in fact existed, because people have been doing experiments on fission for a very long time, since the 1930s, as I said. So what's going on here? Is this in fact the code predicting something which is not likely to be there? There are some possibilities related to the neutron skin, proton-neutron collisions, et cetera. I'm going to mention this again in more detail on a further slide, so I'll just mention. I'll say a little bit more about this in a second, but it's important to note that this prediction is present from the same calculations that give us this prediction. Okay, so prospects for experimental detection. Every time I've talked about this, I have people come up to me and say, okay, great, how could we possibly determine whether you're right or not? So that's a good question. And I have 3 candidates here, really primarily 2 candidates. One of them, but I also want to sort of indicate the difficulties associated with this. So one of them is this distinctive angular distribution. So I have this snapshot from before. We have the ring-shaped cloud around the fission axis, and we have the longitudinal emission in the lab frame. And then we have these as a separate process, we have the fully Coulomb accelerated fragments, which evaporate neutrons isotropically in their rest frame. So these two things should, in principle, look different from the point of view of a detector. So in principle, what one could do was one could figure out what you would get if you had 9 to 14% of this 3-cloud type distribution in the lab frame, and the rest is coming from isotropic emission in the rest frame of the fragments. Figure out how to add those distributions together and try to predict what a detector would see, and then construct such a detector and look for deviations from just isotropic emission. Okay, nice and easy for me to say from the perspective of a theorist, but some of the experimental difficulties associated with this. First of all, you have to know the fission axis, which obviously for us is easy. The fission axis is Z because we choose it to be so. But if you're an experimentalist, you need a detector to detect the fission fragments, and you also need neutron detectors. And it requires simultaneous determination of these two things. So you have to have two detectors operating in synchrony with one another. That's a very difficult measurement, but we know that there are several experimentalists interested in this. Grisha Rogachev at Texas A&M has plans that are in early stages to try to measure this. And at one point in time, we had Lisa Bodka at Washington University in St. Louis, who was also interested in this question, but I believe that effort is no longer ongoing. It is stalled. And again, early days, so it's likely to be years before any of these things comes to full maturity. And then the other thing is the high energy tail. And the high energy tail of kinetic energy per neutron. So as I mentioned, and this is the impossibly tiny figure that I've duplicated on the corner of the slide, there's some small fraction of neutrons which should be emitted with very high kinetic energy, which you could not account for by strictly evaporation from the fragments. So in principle, if you observed a very high energy neutron coming from fission, and there was no other explanation, then that would be strong evidence that you have observed a scission neutron, excuse me. And in fact, there is experimental evidence for fission neutrons up to 30 MeV, with, as far as we know, no other plausible explanation as to what the origin of those neutrons are. And I have that reference here. One of the authors on this paper is Capote, whom we heard this from. And then there's the scission protons, but as I mentioned, we're not super confident that those are there. And I'll say one more thing about this, and I promise I'm almost done. It looks like we're going to end right on the hour. But I will say one more thing in this blue box. An experimental detection would offer a direct window into the fastest timescales in the fission process, which would be kind of cool. I mean, you would basically be observing something that's happening on the tens of Fermi over C timescale. Okay, future work. Scission protons, what's going on here? It's a little bit of a weakness in these results that we've presented thus far, that we have the signal which experimentalists tell us they would have likely already seen. And in fact, they have not seen this. So what's going on here? I mentioned briefly, and I said I would talk about this more, so let's do this now. It's possible that the neutron skin has something to do with this. So this refers to the neutron density towards the outer edge of a heavy nucleus, and it is known that density functional theory underpredicts the width of this neutron skin. And since the neck of the nucleus is primarily supported by neutrons at the moment of scission, it's possible that having a substantially thicker neck, basically, will have a significant influence on the proton dynamics, as those are the ones that fission first. So there's room within the parameters of the seal functional to explore this point, and that is coming up very soon. We hope to see whether that makes any, whether that has an influence. But then there's also more fundamental improvements that can be made to the formalism as a whole. So I tried to make this case that time-dependent density functional theory is this magnificent quantum mechanical approach, and it is. And this is the figure that I was talking about with Yukari earlier, but here we have, this is the potential energy surface. So elongation versus left-right asymmetry of the nucleus, and every color here is sort of the energy of the nucleus at that point. And you see all of these various fission trajectories as they play out on this surface. And they basically form a continuous curve on this surface, which is ultimately sort of a semi-classical description of what's taking place. But we know that fission is a fully quantum mechanical phenomenon, which I hope I've been able to communicate over the course of this talk. So in principle, it should be possible to have interference and entanglement between these trajectories. And this is a new idea that Aurel has had, which we're looking forward to applying to our fission calculations very soon. And it would include ingredients which right now are missing from the code, including proton-neutron correlations, beyond mean field effects, and hopefully this will also mean more accurate calculation of scission neutron properties and things like this. So that is all work to come. And with that, I am out of things to say, and I'm 1 minute over time. So thank you all very much for listening. And if you are willing to stick around, I'm happy to take questions. But otherwise, thank you for coming.
Yeah, thank you for the very interesting talk. And yes, anyone has questions, then please just speak up. Yeah, go ahead.
All right, I see Ulrich first, so go ahead.
Yeah, hello. Can you hear me?
I can hear you, yes.
Good, wonderful. Thanks. I have some questions. One is on the method itself. I was thinking about the inverse process. People ran heavy ion collisions by shooting two heavy or two lighter nuclei, O16 on O16, let's say, together and try to make them fuse in time-dependent Hartree-Fock. It always turned out there was not enough friction in these calculations. The systems would never stick together afterwards. They wouldn't fuse, but they would just go through each other. And the solution for that is that there were sort of two particle interactions missing. Isn't the same effect in your calculations as well missing?
So we have, so this is a point that I probably should have gone over in more detail. The words are on the slide, but I didn't dwell on it very much. We have pairing correlations. I only had this one bullet point to say that it's an extended to superfluid system. So pairing is loosely speaking one of these two particle interactions.
Yeah, but
basically a contact
that's a very
interaction.
special one. Yeah. Okay.
Yeah. I mean, we believe that this particular interaction is relevant here, and that's captured through the introduction of a pairing field. I'm sorry, it's sort of a technical description of what's going on.
Sure.
So we believe that,
except for the pairing, what you're running through is a one body density distribution.
Yes, that's right.
And therefore, you're certainly missing all sorts of other correlations in this game, isn't it?
Yes, I believe that is correct. We have arguments as to why this particular interaction is the one worth including. And apart from this, I don't know what I can say. Maybe somebody will come along and figure out how to incorporate more correlation. I mean, I will say that this extended GCM thing that I mentioned on the last slide will give us a much more correlated many-body wave function, but in sort of an indirect manner.
Can I add one more question on the output on your distribution of protons and neutrons? About 50 years ago, there was a big excitement in the fission community about ternary fission. But at that time, they looked at alphas that came out. And alphas are the particles that show up a lot even in reactors, where they sort of poison the fuel cells and so on. So that's important to get that under control. And I was wondering why you don't look for alphas in this game.
I wouldn't say that we don't look for them. I think that they have to come about by some other means, because we just don't see, like I said, the neutron cloud. One possible interpretation of the neutron cloud is that this thing will fly out with that small proton cloud and it will condense into some nucleus or something like this. I want to stress that we don't even have the capacity to describe that within this approach. But another thing that we don't have here is we don't have fluctuations, and the system has axial symmetry. So I'm now speculating. So don't don't hold it against my collaborators if I'm wrong, but I think it's possible. It seems conceivable to me that some sort of fluctuation could give you an alpha emission, but that's totally excluded from the present
fluctuations,
analysis.
but also the missing correlations probably, because you want to then bind from your neutron cloud and some proton cloud. You want to take four particles and bind them to in alpha. And
right. Yeah. So that's definitely not here.
Okay, good. But it
Yeah.
was sort of interesting. People at that time tried to follow the measured alpha trajectories inside and try to get information on the kinematics at the scission point. So what you're doing is something very closely related to that.
That is interesting. Yeah. Thank you. Okay, George.
Yes. Let me see if I can start a video. Well, never mind. Can you hear me?
We can hear you and see you.
Oh, okay, good. Yeah, well, it's a very interesting talk, Matthew, and but this really turns on its head, I think, what people thought earlier, which was that the angular distributions and energies of the neutrons agreed almost perfectly with them being emitted by the accelerated daughter nuclei. Now, you have an angular distribution of your scission nuclei. Have you tried to see what that would do to the to this statement, adding the two together? Would it still look like it compatible with decays from the fragments?
Yeah, I mean that's a really good question, and it's one that we've received multiple times, and I think it's in some sense we have an obligation to produce precisely such a distribution. I didn't talk very much about these interference effects at the boundary because they don't have a huge impact on the scission neutrons. But one thing that it does make it very tricky to do is to try to estimate precisely what direction the neutrons are going at various points to try to give you just the angular distribution from this process, which you could then try to combine with the boosted angular distribution from the fully accelerated fragments. I mean, in some sense, we should really do this. We did construct some angular distributions at some point that didn't make it into the final publication. But yeah, I mean, if this is genuinely a pathway for experimental detection where you have some small deviation from isotropic emission, the only people who could really say precisely what that would look like is us. So I guess I'm now being recorded saying that, and that puts us in a position where maybe we have to do it. Another thing that's nice is the supercomputers have gotten bigger since the last time we did this study. So maybe we can put it in a slightly bigger box and get slightly better data. But yeah, thank you for raising that point. You're
Okay.
totally right, and we should do that.
Yeah.